Welcome to Talk Tensors.
It is really excellent to be back.
You know, I was looking at the stack of papers we have for today's deep dive, and I had a bit of a realization. Yeah. Usually when we sit down to talk about the quote-unquote next big thing in AI, the conversation follows a pretty predictable trajectory.
Right. The whole bigger is better doctrine.
Exactly. We talk about scale.
Always scale.
We talk about adding more GPUs to the cluster. We talk about data sets that have gone from billions of tokens to trillions of tokens.
And beyond trillions at this point.
Right. And we talk about models that are so large, they basically need their own nuclear power plant just to run a single training cycle.
It is a massive resource sink.
Yeah. The mental image is always this monolithic skyscraper, and we're just pouring more and more concrete on top to see if we can touch the moon.
That has definitely been the dominant trend for the last, 5 or 6 years?
Yeah.
The era of the dense transformer.
But the research we are covering today, it feels different.
It really does.
It feels like a genuine architectural shift. We aren't talking about making the monolith bigger.
No, we are taking a sledgehammer to it.
Exactly. We are talking about taking a sledgehammer to the monolith. We are talking about fragmentation.
Radical fragmentation.
So the paper we are looking at is titled Mixture of a Million Experts, and it introduces a technology called PEER.
PEER, right, which stands for Parameter Efficient Expert Retrieval.
And you hit on the headline number there, which is the million.
Yes, the million.
The million experts. Just to frame this for everyone listening, because mixture of experts, or MOE, is a buzzword you hear a lot lately in the open source community. Mm-hmm. When you see releases like Mixtral, or even the rumors about the architecture of some of the leading proprietary models, you're usually talking about a handful of experts, right?
The standard numbers are surprisingly small, actually.
Like, what are we talking about?
Traditional MOE architectures might have 8 experts.
8.
Maybe 16. In extreme cases, maybe 64.
Okay, so relatively small numbers.
Very small. And for every word generated, the model picks the best 1 or 2. It is essentially a committee.
A committee.
A very small, very overworked committee.
And today we are talking about moving from a committee of 8 to a city of 1 million.
Over 1 million, actually.
Yeah.
And the central argument, the thesis of this entire deep dive, is that the future of AI scaling isn't just about adding more parameters blindly.
Right.
It is about granularity.
Granularity.
We're moving from generalist monoliths to a swarm of hyper-specialized savants.
A swarm of savants. I absolutely love that image. It sounds like a sci-fi novel.
It is mathematically beautiful, too, as we'll see.
So we have a pretty serious roadmap for today. We're going to unpack why our current transformers, the ones you know and love, are hitting a bottleneck that raw scaling cannot easily fix.
A feed-forward bottleneck.
Exactly. Then we are going to tear apart this PEER architecture to understand how you can possibly manage 1 million neural networks without melting your server rack.
Which involves some incredibly clever routing math.
And we have to spend some time on that math behind the granularity scaling law, which is fascinating stuff. It really redefines how we think about efficiency.
It is the theoretical backbone of the whole paper.
And of course, we have to talk about the novel notions segment at the end, because if this architecture works and the data says it absolutely does, it opens up some wild possibilities for how we buy, sell, and trade knowledge in the future.
It definitely changes the economic landscape of intelligence.
Absolutely. So let's start with the status quo. I want to understand the problem before we look at the solution.
Makes sense.
What is the actual structural issue with the way we are building models right now? Why can't we just keep making the dense models bigger forever?
To understand the problem, you have to look at the anatomy of a transformer. Specifically, we need to talk about the feed-forward layers, or FFWs.
Okay. Let's do a quick refresher for everyone listening. In the transformer architecture, you have the attention mechanism and you have the feed-forward network.
Right, those are the 2 main pillars.
How do those 2 interact?
Think of it this way. The attention mechanism is the quote-unquote logic center.
The logic center?
It looks at the sentence the cat sat on the mat and figures out that cat and mat are related. It handles the context, the grammar, the relationships between concepts in your prompt.
Okay, so attention is the connector. It figures out what words care about each other.
Right. But the feed-forward layer, that is the memory.
The memory.
That is the encyclopedia. In a standard dense model, think of your standard open weights model. These feed-forward layers are where the model stores its factual knowledge.
Oh, I see.
When you ask it who won the World Cup in 1998, that information is encoded in the weights of the feed-forward layers.
And these layers are big, right?
They are massive. The feed-forward layers account for about 2/3 of the total parameters in a standard transformer.
2/3.
Yes, they're the bulk of the brain. The vast majority of what you are downloading when you download a model is just these feed-forward layers.
Okay, so what is the bottleneck?
The problem is, in a dense model, every time you want to make the model smarter, you add more parameters to these layers.
Right, you make the encyclopedia thicker.
You add more pages, exactly. And here's the kicker. For every single token the model generates, you have to activate all of those parameters.
Wait, all of them?
All of them.
So if I ask the model, what is the capital of France, and it has 1 trillion parameters?
It has to light up the whole trillion parameter brain just to output the word Paris.
That feels incredibly wasteful.
It is disastrously inefficient. It represents a linear cost relationship.
A linear cost meaning they scale directly together.
Right. If you double the smarts by doubling the parameters, you double the compute cost, the FLOPs.
And the memory usage, right?
And the memory usage for every single forward pass. It is like reading the entire Library of Congress just to find a single recipe for pancakes.
That is a great way to visualize it. I am picturing a librarian sprinting down every single aisle, pulling every single book off the shelf, scanning every page just to find flour eggs milk.
Exactly. And in the world of compute, that sprinting librarian costs electricity. It costs time. It costs money.
So the industry realized this was unsustainable. We cannot keep building bigger libraries if we have to read every book for every single question.
Which is exactly why the mixture of experts, or MOE, came in initially.
Right, this isn't a brand new idea.
Not at all. It's been around for a few years. The first solution was the coarse-grained MOE.
Coarse-grained.
The idea is simple. Instead of one giant dense block of parameters, let's chop it up into smaller blocks. Let's say 8 blocks. We call these experts.
So instead of one giant brain, we have 8 medium-sized brains.
Precisely. And then for any given input, we introduce a router.
A router?
The router is a little neural network that looks at the incoming token and says, oh, this is a chemistry question.
Okay.
Expert number 3 acts like a chemist, so send it there. Or this is a Python coding problem, send it to expert number 7.
And the other experts? The ones that are not picked?
They stay completely dormant. They don't activate. You do not pay the compute cost for them.
So you only activate a fraction of the total parameters. This basically decouples the model size from the compute cost.
Exactly. Decoupling is the key word. You can have a massive model, but it is cheap to run because you are only using, say, 1/8 of it at any given time.
This sounds great. We have seen this work. We know it works.
If it works beautifully up to a point.
So why aren't we satisfied with just 8 or 64 experts? Why is this paper arguing that we need 1 million?
Well, why is the paper arguing that current MOEs are hitting a wall?
Yeah, exactly.
Because of the plateau. The research covered in this paper and previous work shows that the efficiency gains from standard coarse-grained MOEs start to flatline.
They flatline.
You cannot just keep adding huge experts and expect the model to get better linearly.
Why not, though? If 8 is good, isn't 8,000 better? If I have a committee of 8,000 experts, surely I can find someone who knows the exact answer.
Theoretically, yes. But practically, you run into 2 massive engineering walls: routing complexity and load balancing.
Let's unpack routing complexity first.
Think about the router's job. If you have 8,000 large experts, the router has to check all 8,000 to find the best one.
Right.
That search process, finding the top K matches, is usually an O of N operation.
Let's clarify O of N for anyone listening who might not be a computer science major.
Big O notation describes how the difficulty of a task scales.
Okay.
O of N means linear. It means if you double the number of experts, you double the time it takes to search them.
So if I have 10 items, it takes 10 steps. 1,000 items, 1,000 steps.
Exactly. So if you have 1 million experts and you use a standard router, the router has to look at 1 million options for every single word it generates.
That sounds incredibly slow.
It is prohibitively slow. As N, the number of experts, gets really big, the router actually becomes the bottleneck.
Oh, wow.
It takes more compute to find the expert than for the expert to actually do the work.
It is like spending 4 hours trying to decide which restaurant to go to and then eating your meal in 10 minutes.
You spend all your energy asking who should do this job instead of just doing the job.
That makes total sense. So the routing complexity kills the scaling. What was the second issue?
Optimization. Load balancing. It is very hard to train thousands of distinct large neural networks without some of them collapsing.
Collapsing. What does that mean in this context?
It means the router gets lazy.
Lazy.
It starts sending everything to expert number 1 and expert number 2 because they learned a little bit faster early on.
Okay.
And it just ignores the other 7,998 experts.
So they never get used.
You never get used. They never get updated. They become dead neurons, wasted space on your hard drive.
So the field was basically stuck. We knew MOE was the right direction, but we couldn't scale the number of experts up because the router would get too slow or too dumb.
We were stuck at coarse granularity, small numbers of big experts.
And that is the wall this peer paper is trying to smash right through.
But
they're asking, why not a million?
But clearly to do that, they had to reinvent the architecture.
Right. They couldn't just copy paste the old MOE design and change the variable from 8 to 1 million.
That would break the router immediately. They had to redesign the fundamental atomic unit of the network.
Which brings us to peer, parameter efficient expert retrieval.
Let's break down the architecture.
The most shocking thing to me when reading this was the definition of an expert and peer.
It is a complete paradigm shift.
Because when I hear expert, I think of a sophisticated network. I think of a PhD.
In a standard MOE, an expert is a large feed-forward network, maybe millions of parameters on its own. It is capable of processing complex concepts.
Right.
In peer, an expert is a singleton MLP.
A singleton MLP. Translate that for us. What does that actually look like?
It is a neural network with one hidden layer containing exactly one neuron.
Wait, one neuron?
One single neuron.
That is tiny.
Yeah.
That is barely a network. Can a single neuron actually know anything?
That is the magic of this paper. Alone, it knows very little.
Right.
But when you have a million of them, it changes everything. It is the smallest possible unit you could theoretically call the neural network layer.
So how does this single neuron actually work?
The equation they use is beautifully simple. E sub I of x equals sigma applied to the transpose of u sub I times x, all multiplied by v sub I.
Okay, let's unpack the math for a second. I know we try to keep it light, but this equation is the heart of the machine.
Let's keep it visual.
Yes, please keep it visual. What is happening in that formula?
Imagine you have an input vector x, that is the data coming in representing the word or concept you are processing.
Okay.
You project it onto a vector u.
Project onto a vector. That is a dot product, right?
Correct. It is a similarity check. The vector u is like a key.
A key.
This step effectively asks, how much does this input match my specific key? If the input is apple and the key is fruit, the score is high.
And if the key is car, the score is low.
Exactly. So u is the filter.
Okay.
Then you apply a nonlinearity represented by sigma. In this paper, they use ReLU or GELU.
And what does that do practically?
This is the neuron firing. If the match isn't strong enough, if the dot product is negative or too low, the nonlinearity zeroes it out. It says, nope, not relevant.
So it acts as a gatekeeper.
Exactly. And finally, if it passes the gate, you multiply that scalar result by another vector v.
And what is v?
This v vector is the value, the actual knowledge or transformation the expert provides back to the network.
So it is essentially a key value lookup with a nonlinear gate in the middle.
Exactly.
So instead of an expert being a whole department of people, an expert here is one guy with a very specific, tiny piece of information.
I really like the Lego analogy to explain the difference in scale here.
Let's hear the Lego analogy.
Think of a standard coarse-grained MOE as a garage where you have 8 pre-built engines. You have a V8, an electric motor, a diesel engine, a jet turbine.
Yeah.
When a car comes in, you have to swap in the whole engine. It is bulky, it works, but it is not flexible. You get the whole engine or nothing at all.
Right. And if I just need a slightly faster spark plug, I still have to swap the whole engine.
Exactly. Peer doesn't have pre-built engines. It has a giant bin of 1 million Lego bricks.
So Lego bricks being these single neuron experts.
Right. These are the singleton experts. When a token comes in, the model doesn't pick one engine. It dynamically grabs, say, 128 specific Lego bricks and snaps them together instantly.
Instantly.
It builds a custom engine just for that one single token.
That is a massive shift in how we think about layers. Usually we think of a layer as a fixed wall of math.
Yes, a static matrix.
Here the layer isn't a fixed structure. It is assembled on the fly.
Exactly. It is ephemeral. This is the second major design decision. Multi-head retrieval.
Multi-head retrieval. So it is pulling from multiple places at once.
The model doesn't just pick one tiny expert. It uses a mechanism very similar to multi-head attention.
Okay.
It might have, say, 8 heads, and each head retrieves 16 experts.
So 8 times 16, that is 128 active experts for that token.
Correct. So effectively, for that one split second, the model creates a hidden layer of size 128.
Wow.
But that layer is composed of neurons pulled from a shared pool of over a million options.
And because different heads share the same pool, you get this incredible mix and match capability.
The combinatorial explosion of possibilities is staggering.
Like one head might pull experts related to grammar, another head pulls experts related to French history, and another pulls experts related to sarcasm.
Yes.
And they just combine instantly to process the token.
This enhances knowledge transfer significantly. In the old way, the French history expert and the sarcasm expert were separate, large networks that didn't talk much.
They were siloed.
Siloed, perfectly put. Here they are, just neurons in the same soup, ready to be combined in any permutation. You can have sarcastic French history one moment and sarcastic Python coding the next, using some of the exact same sarcasm neurons.
That flexibility is mind-bending.
It is incredibly elegant.
But wait, we have to go back to the bottleneck we mentioned earlier.
The router.
Right. We solved the expert size problem by making them tiny single neurons, but we still have the search problem.
We do.
If I have a bin of 1 million Lego bricks and I need to find the perfect 128 bricks in a millisecond, isn't that search impossible?
It sounds impossible, yes.
You said checking 1 million options is O of n and way too slow. How do they fix that?
They fix it with a technique called product keys. This is the retrieval part of parameter-efficient expert retrieval.
Product keys. This comes from that Lample paper, right? The product key memory paper.
It does. It is a brilliant mathematical trick to completely compress the search space. It allows you to search a massive database without looking at every single entry.
Explain the trick to me. How do I find the needle in the haystack without looking at the hay?
Imagine a grid. Let's say you have a square grid that is 1,000 rows by 1,000 columns.
Okay, a grid.
How many cells are in that grid?
1,000 times 1,000, that is 1 million cells.
Right, so imagine our million experts are laid out on this grid. One expert per cell.
Got it.
Now, normally to find the best expert, you'd have to scan all 1 million cells.
Which is the slow, linear search we want to avoid.
Exactly. But what if instead of scanning the individual cells, you just scan the rows and the columns?
Okay, walk me through that. How does that work?
You generate a query vector based on your input word. You split that query right in half.
Okay.
Use the first half to find the best matching row out of the 1,000 rows.
So you do 1,000 checks.
Then you use the second half to find the best matching column out of the 1,000 columns.
Another 1,000 checks.
Right. And the intersection of that best row and best column points you directly to a specific cell in the grid.
And that cell contains your expert.
Exactly.
So wait, you did 1,000 checks for the row and 1,000 checks for the column. That is 2,000 checks total.
2,000 checks to search a space of 1 million items.
That is insane. You turned a linear search into a square root search. The square root of 1 million is 1,000.
Yes. O of square root of n.
Wow.
If we scaled this to 100 million experts, we would only need to search 20,000 items. 10,000 plus 10,000.
The efficiency gains just get bigger the larger the model gets.
The scaling is phenomenal.
That is incredibly clever. It is like finding a location on a map using latitude and longitude.
That is a perfect analogy.
You don't scan every square inch of the map. You find the latitude line, you find the longitude line, and X marks the spot.
The product keys are essentially the latitude and longitude coordinates in latent space.
And it is crucial to note this isn't a fixed hash table, right? It is not like the Dewey Decimal System where someone decided history is in row 5 beforehand.
No, and this is the learning part of machine learning. It is fully differentiable.
Meaning it updates during training?
It is a learned index. The model learns how to organize the experts on this grid to maximize retrieval speed and accuracy.
How does it organize them?
It naturally groups similar experts together, or perhaps complementary experts. It effectively builds its own internal library sorting system.
So it is like a library that constantly rearranges its books so that the ones you need together are always at eye level, right next to each other.
Exactly.
So we have tiny experts, the singletons, and a hyper-fast way to find them, the product keys.
Yes.
But why does this actually lead to better performance? Just because we can do it, why should we?
That brings us to the theoretical heart of the paper. The scaling law of granularity.
The scaling law of granularity. Let's dig into this. We are all familiar with the standard Kaplan scaling laws. Add parameters, get lower loss.
The whole scale is all you need mantra.
Right. But recently, researchers have proposed a refinement. The fine-grained Moe scaling law.
Yes, let's break down the variables here because they matter. We have P, the total parameter.
Total parameters, okay.
We have P active, which is the parameters we actually use per token.
The compute cost, essentially.
And we have G for granularity.
Okay, P active, and G.
Right. The goal of efficient AI is simple. We want P, the total knowledge, to be as high as possible. We want the brain to be huge. We want to know everything.
Sure.
But we want P active, the compute cost, to be as low as possible. We want to think efficiently.
We don't want to spend $100 to answer a single question.
Exactly. So we want a giant library, but we only want to read one page at a time.
So how does the math solve this?
The math shows that to reconcile these two opposing goals, you must increase granularity G. The formula is roughly G equals P active divided by P expert.
Granularity equals active parameters divided by the size of the expert. Let me think about that.
So look at the equation. If you want to maximize granularity G, but you want to keep active parameters P active low, what is the only variable you can change?
You have to make the denominator key expert as small as physically possible.
Bingo. You minimize the size of the expert.
Oh, I see.
If the expert is huge, granularity is low. If the expert is tiny, granularity is high.
And what is the smallest possible size for a neural network expert?
A single neuron.
Which is exactly what Peer does.
Exactly. By reducing the expert size to the theoretical minimum, Peer maximizes the granularity scaling law.
It pushes it to the absolute limit.
It allows you to have a massive total parameter count while keeping active computation very, very low.
It effectively decouples compute from capacity entirely.
It does.
You can make the model smarter by adding more tiny experts without making it slower because you still only retrieve the same number of them.
That is the promise. It suggests that previous Moe models with large experts were actually horribly inefficient because their granularity was simply too low.
They were activating too many parameters that weren't strictly necessary for the specific token being processed.
Right. It is like hiring a whole law firm when you just needed one paralegal to sign a single document.
The large expert Moe forces you to hire the firm. Peer lets you just hire the paralegal.
Exactly. And you can hire 100 different paralegals from 100 different firms for the price of one partner.
That is a brilliant way to look at it.
It is deeply elegant.
But theory is one thing, reality is another.
Always.
We have seen plenty of papers with beautiful math that completely fail when you actually put them on a GPU. Did they actually build this thing and did it work?
They absolutely built it, and the results are very compelling. They performed an isoflop analysis.
Isoflop. For those who aren't deep in the benchmarking weeds, explain isoflop.
Isoflop analysis is basically the gold standard for fair comparison in AI. ISO means equal. FLLP is floating point operations, essentially compute steps.
Okay.
Essentially, they said, if we give every model the exact same budget of computing power, the same amount of energy, the same amount of time, who learns the most?
It is like a racing class. Everyone gets the exact same amount of fuel. Who goes the furthest on the track?
Precisely. It strips away the advantage of just throwing more money at the problem.
So who do they race?
They compared a standard dense model, a standard Moe with 128 large experts, a product key memory or PKM model, and Peer.
And the chart, what did it look like?
The phrase is down and to the right. In these charts, the y-axis is perplexity.
And perplexity is lower is better?
Lower is better. It literally means how confused is the model by the text. Lower perplexity means it understands language better.
And the x-axis.
Compute budget. Peer consistently achieved lower perplexity than all the other baselines for the exact same compute budget.
And this was on the C4 data set, right?
C4 was the primary benchmark, yes.
Yeah.
Which is a massive web text data set. But they also tested it on the curation corpus lambda, the pile, and Wikitext.
So it wasn't a fluke.
No, it was consistent across domains. On lambda, for instance, which tests the ability to predict the last word of a sentence requiring broad context, Peer shows significant gains.
That is interesting. That suggests it is not just memorizing better, it is reasoning better, or at least modeling the structure of language better.
It is definitely using its parameters more effectively to map out the latent space of the text.
Well, one thing I noticed in the results section, they did some ablation studies to figure out why it was working.
Ablation studies are crucial. You turn off parts of the architecture to see what breaks.
Right, and there was a detail about batch normalization that seemed really important. It felt like a gotcha detail, something that if you missed it, the whole thing would just collapse.
Ah, yes, the dead neuron problem. We touched on this earlier.
Right, with the router getting lazy.
Exactly. In Moe models, a very common failure mode is that the router falls in love with a few experts and ignores the rest.
So you have 1 million experts, but the router only sends work to 50 of them because it got comfortable with them early in training.
And the rest are dead. Wasted capacity.
Like having a massive workforce, but only giving tasks to the 2 guys sitting in the front row.
Exactly. And because the router is learned, once it stops picking an expert, that expert stops learning, which makes it even less likely to be picked later.
It is a vicious cycle.
A very vicious cycle.
So how did they fix it? How did they force the router to use all 1 million experts?
To prevent this, the authors added a batch normalization layer to the query network.
Batch norm. How does that help?
Basically, it normalizes the query vectors, ensuring they are distributed more evenly across the hypersphere of the latent space.
Oh, so it prevents the queries from just clustering in one tiny direction?
Exactly. It forces the router to look at completely different parts of the product key grid.
The result must have been pretty stark.
It was stunning, actually. In their utilization stats, they found that expert usage was nearly 100%.
100%.
Across the validation set, almost every single one of the 1 million experts was getting used.
That is incredibly hard to pull off. Usually you see huge imbalances in these massive architectures.
It speaks to the effectiveness of the learned routing and the product key structure combined with that batch norm trick. The model essentially learned to utilize its entire brain.
Another interesting ablation was the trade-off between the number of heads and the number of experts retrieved per head.
Right. They explored that space thoroughly. They found that increasing the number of active experts retrieving more Lego bricks always helps performance.
But there is a catch, right?
Yes. It has diminishing returns, and it obviously increases the memory cost because you are activating more parameters.
So there is a sweet spot for active experts.
But importantly, and this is totally key, for scaling increasing the total pool of experts going from, say, 250,000 to 1 million improved performance without increasing the inference cost.
Because of the O square root of n search?
Exactly.
You can make the library bigger without making the librarian slower?
Precisely. That is the magic of the granularity scaling law in action. You can add knowledge basically for free in terms of inference time.
I want to pivot to the implications section. We have a model that is more efficient and follows this granularity scaling law.
It is a great technical achievement.
But there is another implication here that I think is even more exciting: lifelong learning.
This is where the expert concept really, really shines.
Because in a dense model, everything is entangled, right?
Completely entangled. If you want to teach a pre-trained model a new fact, say the result of the 2024 Super Bowl, you have to update the weights.
You run back propagation?
Yes. But because all the weights are interconnected, updating them to learn that the Chiefs won might slightly mess up what the model knows about the 1998 World Cup.
Catastrophic forgetting. You learn the new thing, you overwrite the old thing.
Precisely. It is the absolute bane of AI training. It is why we have to constantly retrain models from scratch.
But with peer, you have a pool of 1 million independent experts.
Independent is the key word. If you want to learn new information, you don't necessarily have to touch the old experts at all.
You can freeze them.
You can freeze them completely.
And just add new experts.
Exactly. You can just expand the pool. You add another 100,000 tiny experts trained specifically on the new data stream.
And the router just figures it out.
Because the router is a learned search index, you can learn to route relevant queries to these new experts without disturbing the old ones.
So the model maintains plasticity. It stays flexible over time.
It creates a real path toward models that learn continuously, instead of the current paradigm, which is training run deployment obsolescence. You have training run deployment, constant growth.
It is like adding new books to the library. You don't have to burn the old books to make space on the shelf.
And because the experts are so small, just singletons. MLPs adding them is incredibly cheap.
Right. You aren't adding massive distinct neural nets. You're just adding rows to the expert table.
It is highly modular.
I also want to clarify the difference between peer and PKM, because they use the same retrieval trick, the Cartesian product keys.
They do share that routing mechanism, yes.
So why is peer better? Why not just use memory?
Great question. It is a subtle but critical distinction. PKM retrieves static values.
Static values, like a lookup table.
Exactly. You put in a query, you get out a fixed vector. It is essentially a memory bank.
Okay, so it is fetching a noun. It is fetching a fact.
Right. Peer retrieves experts. It retrieves a function. E sub I of x is a calculation, not just a static value.
It takes the input x and actually transforms it.
This makes peer much more expressive. It is not just remembering facts. It is remembering how to process information.
Oh, I see. It is the difference between looking up an answer in a book and calling a guy who knows how to solve the problem for you.
That is a perfect analogy.
Right.
PKM is a book. Peer is a consultant.
A consultant takes your specific context and applies their knowledge to it.
A book just says what it says, regardless of your context.
So we have a million consultants, we have ultra-fast routing, we have granularity scaling. It really feels like this is the architecture that takes us from big AI to deep modular AI.
It certainly suggests that the monolith is dead. The future is highly modular.
Which perfectly brings us to my favorite part of the deep dive, the novel notions segment.
Let's hear them. I'm ready.
Quick disclaimer for the listeners. This is the part where we take the factual technology we just discussed and extrapolate it into the realm of the outlandish but plausible.
Purely for entertainment purposes.
Exactly. These ideas are not in the paper. These are what-if scenarios. Idea number 1, the App Store of experts. Or maybe we call it the modular brain marketplace.
I like the sound of that.
So Peer proves that we can have a shared pool of a million tiny distinct experts, right? And the router just learns to pick the right ones.
Yes, the pool is just a collection of decoupled parameters.
Currently, if I want to fine-tune a model for, say, medical law, I have to take a base model and run a LoRa or a full fine-tuning path.
Which is a heavy process. It takes GPU hours. It is messy.
Right. And you usually end up with a completely separate model checkpoint.
Yes, a whole new set of weights.
But with Peer, what if I could just buy a packet of experts, let's say 50,000 singleton experts that have been trained specifically on the U.S. Code of Federal Regulations.
Interesting.
I download this file. It is really just a weight matrix. I inject these 50,000 experts into my model's existing pool of 1 million. I don't retrain the backbone at all.
You would need to update the router to index them, but yes, theoretically.
The cost would be trivial compared to training a model.
You are essentially grafting new brain tissue directly onto the existing structure.
Suddenly, my model just knows medical law. It physically added neurons to its brain. It is like in the Matrix. I know Kung Fu.
You aren't training the model. You are slotting in a cartridge of pre-trained neurons.
It creates a completely plug-and-play ecosystem. You could have vendors selling high-quality expert packs.
A Python coding pack, a creative writing pack, a quantum physics pack.
Exactly. And because they are singleton experts, they are hyper-granular. You could mix and match.
Customize your intelligence.
I want the Python pack and the sarcastic tone pack, but I want to disable the political opinion pack.
You just delete those specific experts from the active pool.
It fundamentally changes the business model of AI. You aren't selling a monolithic model, you are selling the neurons that populate it.
It solves the copyright issue too, potentially.
Oh, how so?
If you want the New York Times style expert pack, the New York Times sells it to you directly.
Oh.
You plug it in and your model writes exactly like their journalists, and they get paid for the neural structure they trained.
That is a game changer. It completely decentralizes the intelligence.
This is a very powerful idea.
Okay, idea number 2. The infinite context via expert allocation. I call this the temporal specialist.
Ooh, temporal specialist. I really like the name.
We always complain about contest windows, right? Oh, the model forgot what I said 10,000 tokens ago.
A classic problem.
Yeah.
Even with retrieval augmented generation, it is imperfect.
Right. The model reads the old text, but it doesn't really remember the feeling or the subtext of the conversation.
It's just recalling strings.
So what if we connect lifelong learning directly to the context window? Imagine a model that for every conversation it has with you generates new singleton experts on the fly.
Generating experts during inference.
Or during a micro-training step in the background. As we talk, the model trains a tiny expert, just one neuron or a small cluster, that physically encodes the vibe and the facts of our specific conversation.
So it is not storing the conversation in a temporary buffer. It is actually encoding it into the weights.
Yes, it creates a session expert. And it throws that expert into the pool. 2 weeks later, I come back. I say, remember that idea we had?
The router scans the pool, finds the session expert from 2 weeks ago via the product keys, and activates it.
That is essentially using the neural weights as permanent long-term memory storage.
That would scale to infinite users.
You have a base model, and then for every single user, you have a cloud of 500 tiny experts that represent their specific relationship with the AI.
That would solve the ultimate personalization problem.
The model literally grows a unique substructure for every single person it interacts with. It stops recalling text and starts remembering you.
That is both profound and slightly terrifying.
Isn't it?
It blurs the line between the base model and the user's data in a very permanent way. But structurally, With an architecture like Peer, it is entirely possible.
That is the sweet spot of novel notions. Plausible, but wild.
It certainly is.
Well, we have covered a massive amount of ground today. We moved from the bottlenecks of dense monoliths to the Lego brick architecture of Peer.
We unpacked the math of granularity and the absolute magic of product key retrieval.
The takeaway for me is really that simple equation. Granularity equals active parameters divided by expert parameters.
It's a compass pointing toward a future where models are vast, sparse, and incredibly granular.
And it leaves us with a final thought for the audience. If the human brain is a massive collection of specialized modules, which neuroscience strongly suggests it is Peer, the moment AI architecture finally stopped trying to be a singular mathematical function and started trying to be a society.
A society of neurons. I think that is exactly what it is.
A society of neurons. We will leave you with that image to mull over. Thanks for listening to Talk Tensors.